In this section, we will go over and explain homework problems from chapter 9. The first problem that I'd like to go over would be number 21 and page 375. So let me write down that question number 21 and A. The question is, how many non-bonding electron pairs are there in each of the following molecules? Say we're trying number 21A. You have CH3 and sulfur, dimethyl sulfide. So that's the name of the compound. In order to know how many non-bonding electron pairs are there, you'll have to first draw the Lewis structures. It would be a lot faster for you if you follow the instruction that I'm going to give you now for organic compounds or organic groups. In this case, mostly it's a group with carbon. Now those compounds, carbon would like to have 4 bonds. And with that in mind, you can quickly write down Lewis structure. So let me do that. Now I know that carbon must have 4 bonds. So let's have carbon, 1, 2, 3 hydrogen. And 4th bond has to be with sulfur. Then I have another carbon, 1, 2, 3. So that gives 4 bonds around each carbon. And having 4 bonds around carbon means it has 8 electrons around each carbon. Now let's focus on sulfur. The way I have drawn the Lewis structure, sulfur has 4 electrons. And sulfur is one of those elements which would like to have 8 electrons. So let's have 2 pairs of electrons. So we drew quickly this Lewis structure. You can always verify this by counting valence electrons and assigning those electrons. Keep in mind, hydrogen cannot have more than 1 pair of electron or 1 bond. So in part A, number of non-bonding electron pair, let me highlight them, 1, 2. So there are 2 non-bonding pairs, electron pairs. So that's 21A. Let's try 21B. Again, the question is how many non-bonding electron pairs are there in each of the following. So question is HCN. Again, I have carbon here. So let's first write down HCN. So each having 1 bond. That's how we combine all these atoms together. Now, remember that carbon, in neutral compound, carbon would have 4 bonds. Now, carbon has here 2 bonds, and hydrogen cannot have more than 1 bond. So obviously, all the 3 bonds will have to be between carbon and nitrogen. So this gives carbon 4 bonds, hydrogen 1 bond as expected, and nitrogen now has altogether 6 electrons around. But it will like to have 8 electrons, so I must have 1 electron pair here. And that's the non-bonding pair. So you have 1 non-bonding electron pair. Now if you want to do number C, should not, again, by now you probably know how to quickly write down the structure. H2C2. What I would do, there are 2 carbons, I'd write down carbon back to back and distribute 2 hydrogens evenly among those 2 carbon. So let's have 1 hydrogen here, 1 hydrogen here. So that makes C2H2. And hydrogen has a single bond, and that's what it is expected to have. Now each carbon has now 2 bonds, and we know that it must have 4 bonds. So only way I can give 4 bonds would be by having triple bond. So this is now the structure, Lewis structure for H2C2. This is a quick way of writing down Lewis structure when you have carbon involved. Now, is there any non-bonding electron pair? No, there is no non-bonding electron pair. So hope you understood this. Now we are going to do another problem, which is number 28A. Let me read the question for you. Draw the Lewis structure for each of the following molecules or ions and predict their electron domain and molecular geometry. So in this case, you need to write in both electron domain and molecular geometry. We'll begin with AsF3. AsF3, arsenic fluoride. Again, before we write down the structure, you must have valence electrons. So arsenic is in the same group as nitrogen. So you look at the periodic table. Sometimes this helps. And normally, that group 1A has 1 valence electrons, 2 has 2 valence electrons, 5 would have 5 valence electrons. That's how it goes. Or you just count S and P electrons. Okay, so now arsenic has 5 valence electrons, so that's 5 coming from arsenic, and they have one of them. And each fluorine has 7, and there are 3 fluorine. So altogether we have 26 valence electrons. So valence electrons. Now my central atom is going to be arsenic. Normally the element that's present in least number would be the central atom. So let's have now 3 fluorine. And now I'm going to give noble gas configuration to the outer atoms, which would be 8 electrons. So I must have 6 electrons assigned. So that gives me 8, 8, 8. So I have 24 electrons assigned. I have 2 more electrons left. And you cannot put those 2 more on any of the fluorine, because fluorine already has 8 electrons. So I must put it on arsenic. So arsenic has 4 electron pairs on the central atom. So 4 electron pair around the central atom. Now keep in mind that this question is asking for electron domain geometry and molecular geometry. With 4 electron pair, electron domain geometry is going to be tetrahedral. Electron geometry is going to be tetrahedral. Molecular geometry is not going to be tetrahedral because all these electron pairs are not bonded. So molecular geometry, in order to determine the molecular geometry, think about a tetrahedron with one end missing. And remember that how it would look like? It would look like trigonal pyramidal. So molecular geometry is trigonal pyramidal. And these angles are close to 109.5. So keep that in mind, how I came up with this answer. Now we are going to do number 28E. So let's draw a line here. Now we're going to do 28E. Here the question is, again, it's the same kind of question. Predict the electron domain and molecular geometry. E is XeF2, xenon difluoride. So we are first going to write down the valence electrons. Xenon is a noble gas, so just like any noble gas other than of course helium, you have outermost 8 electrons coming from xenon, and fluorine would have 7 electrons from group 7 and times 2 because there are 2 fluorine, that's 14. Altogether, we have 22 electrons, 22 valence electrons. Keep that in mind. These are outermost electrons. Now, let's draw central atom. X is the central atom. And I don't know the shape at this time, so let's draw any way you want. And Lewis structure doesn't care about shape. So now, assign electrons so that outer atoms have noble gas configuration. So basically, I need to put 6 additional electrons around fluorine so that each fluorine would have 8 electrons. Now I have assigned a total of 16 electrons. Now I need to put 6 more electrons. Now if you need to break noble gas configuration, always keep in mind, break it for the central atom. What tells me that I can have those 3 pairs of electrons on the central atom, even though central atom is now exceeding 8 electrons. When you have extra electrons and there is nowhere else to put, then break noble gas configuration for the central atom. So now I have, around the central atom, I have 5 electron pairs. And 5 electron pairs means electron domain geometry is going to be, let me show you how it would look like, trigonal bipyramidal. So that's electron domain geometry, trigonal bipyramidal. And in order to get the molecular geometry, you need to write down, now there's more than one possibility, but the best structure would be this. And we have 3 pairs in here. So 2 pairs are bonded to fluorine. Now, how do I know out of this several structures why this is right? We know it either by applying 90-degree lone pair interaction, lone pair bond pair interaction, or bond pair interaction that I discussed before. Or you simply remember that when there are 5 pairs of electrons and you have only 2 atoms bonded, what is the best structure? The best structure is going to be a linear molecule because you cover those electron pairs which are not bonded to anything. So if you take the picture of the molecule, it would look like a linear molecule. So electron domain geometry, let me write down here, electron domain geometry is trigonal bipyramidal. I don't have enough space here. Now molecular geometry is linear, because in order to get molecular geometry, cover those electron pairs, because as if you're taking picture of the molecule where you can only see the atoms and their bonds but not those electron pairs, as if nothing else is there. Now we're going to do number 34. This is coming from page 375. Now the question is about NH2 minus, let me write down, NH2 minus NH3 and NH4 plus bond angles. And the question is why bond angles, like in case of NH2 minus is 105 degree. In case of NH3, it is 107 degree. And NH4 plus is 109 degree. So you need to explain that. In order to explain that, first you need to write down Lewis structure and then the shape. NH2 minus, let me show you one such calculation. Number of valence electrons, nitrogen, if you look at periodic table, nitrogen coming from group 5. So group 5 elements have 5 valence electrons or 5 outermost electrons. So 5 will be coming from, so this is what we're calculating now, NH2 minus. Each hydrogen would have 1 electron, and we have 2 of them, that's 2 electrons. So that gives me 2 here and 7 valence electrons. But NH2 has a -1 charge. So there is an extra electron you must add. So overall, you have 8 electrons. In the same way, you can do valence electron calculation for NH3. NH3 again, 5 would be valence electron for nitrogen, 3 for 3 hydrogen, so it'd be 8. NH4 plus would have 5 from nitrogen and 4 from hydrogen, and then you subtract 1 because it's plus. Plus means you take away 1 electron. So in each case, you have 8 total valence electrons. Now let's draw the structure of each one. N, H, H. Now hydrogen cannot have more than 1 bond, so that's fine, but rest of the electron has to go to nitrogen. I have assigned 4 electrons, then I need to assign 4 more. 6, 8. So that's NH2 minus. In the same way, I can write down now NH3. That assigns 6 electrons, so pair of electron has to go to nitrogen. That way nitrogen also gets 8 electrons. NH4 plus would have nitrogen and 4 hydrogens. That's NH4 plus. Now the question is why there is a variation in angle. So let's go over this. In each nitrogen, there are 4 pairs of electrons around. So hybridization in each case is going to be sp3. sp3, sp3. We mentioned that sp3 hybridization goes with 109 degree, 109.5 degree. So in each case, you'd expect around 109.5 degree. But as I mentioned before, whenever you have unshared electron pair, they squeeze the angles of the other atoms. So in other words, in this case, you'd expect smaller than 109.5. Same is the case with the first one. First one has even 2 unshared electron pairs. So there'll be bigger effect of these unshared electron pairs. I'm talking about these electron pairs. And they're going to squeeze this angle between hydrogen, nitrogen, and hydrogen. So it is also expected to be smaller. Now, so indeed, in case of NH2 minus, it is the smallest because of 2 unshared electron pair and 105 degree. Now NH3 has 1 unshared electron pair, which is 107 degree, given the expected to be smaller than 109.5, and so experimentally indeed scientists find that it's 107 degree, and NH2 minus is 105 degree. For NH4 plus is 109 degree, so it's quite the expected value. Now we're going to do number 44C. So this is 44C, and that's coming from page 376. So page 376, Brown, Lemay, Barston, 12th edition book. The question is, predict whether each of the following molecule is polar or non-polar. So I'm randomly picking 2 such problems. One is 44C, the other one I want to do would be 44F. Now 44C, the question is on FF4. Again, first write down the valence electrons. Now sulfur is from the oxygen family, and so it would have 6 valence electrons. Keep that in mind. The group 6 there would also have 6 valence electrons, or 6 outermost electrons. So sulfur has 6. Each fluorine has 7 because it's from group 7A, and there are 4 such fluorine. That's 28. Altogether, you must have 34 electrons. I must account for these 34 electrons. So 34 valence electrons. Now let's write down the central atom. The atom which is present in least number is the central atom. And let's put down the other atoms. Right now we don't know the shape, so I can write down any way I want. 2, 3, and 4. Now we need to work on outer atoms, give noble gas configuration, and fluorine can have 8 electrons. Already we have 2 electrons, so I need to put 6 more. 6 more. Each line is a pair of electrons. So now let's count. At this point, after you give noble gas configuration to outer atoms, now you count total electrons that you have assigned. 8, 8, 8, 8. That's 32 electrons. But we have 34 electrons, so 2 more electrons we need to add. And that has to be added to the central atom. As I said before, if you need to break noble gas configuration, break it for the central atom, not the outer atom. So now sulfur has 5 pairs of electrons around. Now remember, this question is on polarity. So now we need to draw the shape, because depending upon the shape, the answer could be different. With 5 pairs of electrons, this would have trigonal bipyramidal electron domain geometry. So let me show you that. I have this trigonal plane, sulfur in the middle, and this is trigonal bipyramidal with 4 sulfur. The best structure, you have more than one possibility. Again, I explained that before, that why certain structure is more stable than the other. I can figure out that based on 90-degree interactions that I discussed before, or you can simply remember that with electron domain geometry of trigonal bipyramidal having 4 bonded atoms, what is the best shape? The best shape would be seesaw, and that would look like this. 1 fluorine, 2 fluorine, 3, 4. So that's how you can get this. And now let's figure out whether it's going to be polar or non-polar. Sulfur-fluorine bond is a polar bond. Fluorine is more electronegative than sulfur. Just by knowing their location in periodic table, I can tell that, because fluorine is on the right hand side and sulfur is under oxygen, even less electronegative than oxygen. So fluorine is pulling electron away from sulfur, so there'll be an arrow like this. That's dipole moment. Let's put down all these arrows. Second force, third dipole moment, fourth dipole moment. Question is, are they going to cancel out? Answer is no. The force that is going upward and downward, let me highlight them. They would cancel out. So this one is going to cancel out with this, but the other two at an angle of 120, they're not going to cancel out. Think about sulfur represents a table and one person is pushing it at this direction. The other person pushing is at this direction. They're not equal and opposite. So yes, table is going to move along this direction. So let me show you along this direction. So in other words, there is a net effect. And this is going to be a polar molecule. The other way to understand this would be, if it is a highly symmetrical shape and every electron pair is bonded, then they're all going to cancel out. If I had one additional fluorine, in that case I would have had SF5, it would be nonpolar, because then it would have highly symmetrical geometry and all these forces would cancel out. Now I'm going to do another problem. As I said, it's going to be 44F. So let's do 44F. N44F, you have GaH3. So GaH3. Now first we need to write down valence electrons. If you look at periodic table, gallium is right underneath aluminum or boron in the same group as boron. That means it has 3 valence electrons. So valence electrons of gallium is 3 valence electrons. Each hydrogen has 1 valence electron. Now 3 hydrogen would have 3 valence electrons, and altogether there are 6 valence electrons. Now let's write down now the structure, gallium with 3 hydrogens. At this point I don't know what could be the shape, so just write down any way we want. Gallium, hydrogen, hydrogen, hydrogen. Now let's count number of electrons. I already assigned 6 electrons and I don't have any other electron. So in that case there isn't any leftover electron to be placed on gallium, so gallium would only have 3 pairs of electrons. So what could be the shape? With 3 pairs of electrons, the shape is going to be trigonal planar. So it's not the right shape, so it's going to be like this. Gallium, 1 hydrogen this way, another hydrogen this way, another hydrogen this way. And angles are 120 degrees. Now, next we need to know which one has greater electronegativity. Gallium, of course, if you want, you can get help of electronegativity table. So let me show you from electronegativity table on page 299. You find that hydrogen is significantly more electronegative. So hydrogen electronegativity is 2.1 and gallium is only 1.6. So since hydrogen is more electronegative, it's pulling electron away from gallium. So that's one force. Second force, third force. Again, this is highly symmetrical geometry. This is trigonal planar, and they all cancel out. So this is going to be nonpolar. So keep something in mind. For highly symmetrical molecular geometry, all these forces, dipole forces, would cancel out if it's the same element bonded. And this symmetrical geometry could be linear, trigonal planar, trigonal bipyramidal, octahedral, and so these are the symmetrical geometries. I would like to go over number 56, B and D. So number 56, B to begin with. Let me read the question. And in number 56, the question is, what is the hybridization of the central atom? In B, it is HCN. So you first need to write down the Lewis structure. Again, we have carbon now, so I can really save my time by knowing the fact carbon must have 4 bonds. So let me, without even counting electrons, now I first write down central carbon, 1 hydrogen and 1 nitrogen. Now I know that hydrogen cannot have more than 1 bond, so I cannot make multiple bonds on the side hydrogen is bonded. But I must give 4 bonds to carbon, so carbon must have 3 bonds on one side. So that gives 4 bonds to carbon. Now nitrogen doesn't have noble gas configuration because around nitrogen there are 6 electrons and we must have 8 electrons. So you must assign a pair of electrons. So now I'm done with the structure of HCN. Now we need to know the hybridization of the central atom. Central atom is carbon. Question is, around carbon, how many electron domains we have? There are 2 electron domains we have. One is the triple bond, that's considered to be 1 electron domain because all these 3 bonds are directed towards nitrogen along the same direction. The second domain is the electron pair that's binding hydrogen. So there are two electron domain, or behave like two electron pairs. So you must have sp hybridization. Remember, for each electron pair you need one hybrid orbital, so sp would give you two hybrid orbitals, and angle would be 180 degree. And we drew the structure right because this angle is 180 degree. Now let's try 56D. Let's draw a line here. In 56D, question is, what is the hybridization of the central atom in tellurium chloride, TeCl2? Now let's count valence electrons. Tellurium. Now tellurium is in the same group as oxygen, and that's in group 6A. That should have 6 valence electrons. So 6 valence electron. Each Cl has 7 electrons, and 2 of them would have 14. So altogether we have 20 valence electrons. 20 valence electrons. Now let's write down the structure. Tellurium, put down 2Cl. We don't know the shape yet. Of course, for hybridization, you don't need to worry about shape, but hybridization would lead you to the right shape and right angles. So now, tellurium dichloride. Now let's give noble gas configuration to Cl. 2, 4, 6. 2, 4, 6. So I have assigned 16 electrons. So rest of the electrons will have to go to tellurium. So 18, 20. So that's the extra electrons. So now tellurium has, around tellurium there are 4 electron pairs. Remember, for each electron pair you need one hybrid orbital. 4 electron pair you need sp3. And sp3 goes with 109.5 degree. Of course, this question is not asking for angle. This would be squeezed in case they're asking for angle, squeezed and becomes smaller than 109.5 because of 2 unshared electron pairs. These are the unshared electron pairs. About hybridization, let me remind you again before you move to the next problem. This is how you figure out. First write down S, Px, Py, Pz, and all these d orbitals later on. If I have 2 electron domain, then these 2 I need to hybridize, so it'd be sp. If I need room for 4 electron pairs, I'm going to combine these 4. That would be sp3. So this is how you determine what kind of hybridization you'd have. And keep in mind, sp hybridization goes with 180 degree, sp2 120, sp3 109.5. Of course, if there are unshared electron pair, then those angles would be shorter than expected. Now we are going to do number 61. So that's chapter 9, number 61. Let me read the question. Draw Lewis structures for C2H6. So let me first write down the formula. C2H6, C2H4, and C2H2. So first you need to draw Lewis structures, and then you need to write down hybridization and how many sigma and pi bonds are there. And also you need to predict whether any of these would be a planar molecule or not. Now, since these are carbon compounds, I can quickly write down these structures. First, 2 carbon will be bonded to each other, then distribute hydrogen evenly. So each carbon would have 3 hydrogens. 1, 2, 3. 1, 2, 3. And now each carbon has 4 pairs of electrons, or 8 electrons. In another way of looking at it, each carbon has 4 bonds. So it's the right Lewis structure. Let's try C2H4. Again, first I'm going to draw 2 carbon and distribute 4 hydrogens evenly. So 2 per carbon. So I have assigned all these 4 hydrogens, but look at carbon. Carbon has only 3 bonds. So in order to satisfy each carbon, make a double bond. So now each carbon has 4 bonds in C2H4. Now after writing structures, then we're going to write down the hybridization, because the question 61 is asking for Lewis structure, then hybridization, and then predicting what kind of shape it would have. Carbon, 2, and hydrogen. Now again, carbon has 2 bonds. Now make it 4. So that would be triple bond. So that would give you a correct structure for C2H2. Now let's get hybridization. For the first molecule, each carbon has 4 pairs of electrons, so it would have sp3 hybridization. Second one has 3 electron domain, because double bond would be counted as a single electron domain. So having 3 of them, each of these carbon would be sp2. And keep in mind, sp3 hybridization goes with 109.5 degree, or around 109 degree. sp2 goes with 120 degree. And in third case, the triple bond would be like a single domain, electron domain, so there'll be 2 pairs, it'll be counting as 2 electron domain, and then it'd be sp, that goes with 180 degree. So this is 180 degree. This is also 180 degree. Now we need to write down how many sigma bonds we have in each case. In first molecule, they're all sigma bonds, because remember, pi bond gives you the double bond or triple bond. So this sigma bonds, so I have 1, 2, 3, 4, 5, 6, 7. So in first molecule, I have 7 sigma bonds. In second molecule, I have all these carbon hydrogens are sigma, so 4 carbon hydrogens are 4 sigma, and then one of these bonds is sigma between carbon and carbon. Even though it's a double bond, they look alike, but one is sigma, one is pi. So altogether we have 1, 2, 3, 4, 5 sigma and 1 pi. In last molecule, each carbon hydrogen is sigma bond, so that's 2, and one of these 3 bonds in between is a sigma bond. Let's show you that. So now we have 3 sigma, and other 2 making the double bond would be 2 pi bonds. So keep that in mind.